Hey everybody, I'm here in the parking lot behind the Hostler and Dyke buildings, and we're going to be meeting with Professor Sridhar Anandakrishnan, who's a professor of glaciology and geophysics. He's going to be taking us to see the ice cores, which are in the freezer, which is located right here in this area that you've probably never seen before on the Penn State campus.
So hi, my name is Sridhar Anandakrishnan. I'm a professor in the Department of Geosciences here at Penn State. I'm a glaciologist, which means I study glaciers, mainly glaciers in Antarctica and Greenland. And the type of techniques that I use to study glaciers is something mainly called geophysics, and that's a word that means using physical properties of the Earth to understand the Earth. And what I mean by physical properties, things like the mass of these materials, the speed at which sound waves travel through them, the magnetic properties of them, how they deform and things like that. The ice core is like a journal. Every day, snow falls on top of the ice sheet. And for the most part, it just stays there. Because it's so cold, it doesn't melt and run away the way run off the way the snow around here might. And then the following day, more snow lands on top of that. And the following day, just like a journal that you're writing on, where you have a page with some deep thoughts from one day, and then another page with more deep thoughts from another day, the glacier does the same thing. There's a layer of snow from one day, and a layer of snow from the following day, and the following day, and so on and so forth. And those layers just get stored in the glacier. And not just for day after day, but century after century, millennium after millennium, and in some cases, tens, hundreds of thousands of years. That's what we go and we look at. So we're peeking into the journal that nature, climate, and the glacier have written for us. And in the same way that you have deep thoughts that you've stored in your journal, and over the years you've built up a stack of journals, and you can go back and find a page from 10 years ago that was telling you what you did in high school or elementary school, we can drill down through the glacier and pull up a chunk of ice that was put on the glacier 40,000 years ago. And that chunk of ice tells you what the atmosphere looked like then, tells you what the temperature looked like then, tells you what kinds of particles there were swirling around in the air, because all those things landed on the snow, and then more snow landed on top of it. And the glacier that I'm talking about, the ice core that I'll show you, is almost 3 kilometers, 2 miles thick. And I'll show you a chunk of ice that was pulled up from 2.2 kilometers, about 1.5 miles down below our feet. So you're standing on top of this vast glacier, and you just have layers and layers, pages and pages of record from the past, and we've pulled up all of those records, and we can read that record to tell us what past climate looked like. All right, hi, we're in the ice core lab. It's just a great big freezer. You might see these in industrial settings like ice cream plants and stuff, but let's go take a look at it first, and then we'll talk through it. Great. So the ice core lab has 2 rooms. The outside is at a balmy 10 degrees Fahrenheit, and the inside is kept at minus 30 Fahrenheit to keep all the ice cores well frozen. So these are some of the ice cores that we have. This is an ice core that was taken in Antarctica at a place called Waste Divide. This is at a depth of 2,200 290 meters. So that's almost a mile and a half down through the ice at the bottom of, well, about 2/3 of the way through the glacier. And so you drill a hole and you pull up a chunk of ice that, as you can see, is about 4.5, 5 inches in diameter. And it comes up in sections, and then you go down and pull up the next section and so on. And this one contains within it ice that was laid down on the surface of the glacier about 40,000 years ago. And that's why we go to the effort of extracting this ice core, storing it in this cold building, because we want to analyze what the world looked like 40,000 years ago. And this ice core holds clues, evidence about what the atmosphere was like, what the temperature was like, what kind of dust or pollutants or particulates there was in the air. And so we can look at the effect of humans by comparing ice from 40,000 years ago and the atmosphere from today. So there's a number of analyses that we carry out on these ice cores. And the one that sort of gets the most attention and is extremely important is to figure out what past temperatures looked like. What we do here at Penn State is slightly different. And what I want to talk to you about is the flow of glaciers. So all of you know glaciers move, and you'll probably heard the phrase moving at a glacial pace, meaning that moving very slowly like a glacier. And that's because glaciers are solid. They're made of solid ice. And yet, because of the huge mass of solid ice, there's enough forces on that ice that it actually flows almost like honey or a very thick viscous material that, Vaseline or something like that. It can flow across the landscape. All right, so to understand glaciers in the Earth climate system, we need to understand that flow. You all have seen pictures of snowflakes. There are these beautiful hexagonal, lovely pieces of art. But the important thing about them is that hexagonal shape to them. So ice, the ice sheet, a glacier, is made up with billions and billions of these tiny hexagonal crystals of ice. And because the ice crystals are sort of, you can imagine them as being these flat hexagons, when you try to push one ice crystal past another, depending on whether the ice crystals are jamming into each other or sitting nice and smooth one on top of the other, the ice flows more easily or in a more difficult way. And so one of the things we need to know is what is the orientation of all of these ice crystals within the lattice of the glacier, because that allows us to know how easily the ice will flow in response to the forces that are trying to make it flow. And one way you can do it is by taking that ice core and sending a sound wave through it. And measuring how long it takes for that sound wave to travel through. So we've got an instrument that all it does is just make a sound at this end, bing, and an instrument at this end that listens for it, and then we measure how long it takes. Well, what does that tell us? It turns out that these ice crystals, if they're all sitting the way my hand is right now, flat, then sound will travel through them at one speed. Whereas if all the ice crystals are sitting this way, or if they're all jumbled up, then sound will travel at a different speed. And so it's difficult to go in and understand or figure out what the orientation is by just looking at the ice. And so what we do is we use this acoustic, it's sort of like an X-ray, but we use sound instead of X-rays to kind of get a picture of what the interior of that chunk of ice is. And we do that in the laboratory, and we do that on the glacier itself. We go out there and we set off small explosive charges that generates a big boom instead of a little ping that we might do in our laboratory that only needs to travel, you know, a few inches from the source to the receiver. In the field, we need sound that travels 2 miles down and then 2 miles back up, and so we need a big boom instead of a little ping. But the idea is the same. Sound traveling through the ice travels at different speeds depending on what the orientation of these crystals is, and that tells us a lot about how the glacier is going to respond to flow. And that's what I do, that's what my colleagues here, well, one of the things that I do and that my colleagues here do, because we build numerical models, computer models of flow of the glaciers. Because what we want to do is to run the world out 100 years from now and say, what does this glacier look like in 100 years' time? Well, in order to do that, we need an accurate model of the flow of that glacier so that we can change temperatures, change snowfall, and say, oh, what's the effect of that? And to do that, we need to know the orientation of the ice crystals very accurately. And so that's sort of my connection to all of this.